One other thing that we need to know that before starting to name organic, inorganic compounds, especially the ionic compounds, that's what we say we are going to start with. Um, Before we get to that, we need to actually break it down into the various components before we do that. We know ionic compounds is formed between ions. So basically, it's going to be positive ions and negative ions. We said from previous sessions that positive ions, mostly the basic source of positive ions is from the metals, and then the basic source of negative ions is from the non-metals, right? So today we'll be focusing on the metals, right? So metals are the basic source of um, positive ions. We say basics before because sometimes you can have the positive ions coming from a combination of non-metals. If the non-metals combine together, or the non-metals combine together, I can give you a positive ion. Example, ammonium ion, NH4 plus, NH4 plus, right? That one can give you something as positive. So that's an ion, that's a positive ion, all right, but it doesn't come from metal. But that's why I'm saying that the basic source of where you can easily see get the source of positive ions is from the metals, and the basic source is the non-metals, right? Yeah. So also I say basis for the non-metals as well, because there is a combination of non-metals that can give you a negative ion. We call them complex ions. All these one we call them complex ions. So you have SO42 minus. SO42 minus is a combination of all this, and then it's going to come from non-metals, combination of non-metals forming that negative ions, right? So when I say basic source, I hope you get it now. So now let's talk about the metals, which are the basic source of positive ions. This ion formation, before they can form a bond, we say they form ions. Why is it necessary? Why can't they just bond, right? We do all this bond to attain stability, but then why should the electrons be transferred in ionic bond? Because ionic bond, we said the compound usually we have to transfer electron from the metals or the positive ions to the non-metals, which are the receivers. Okay, so why should this happen? The thing is, because I'm the oxidation number. Oxidation number is when we are going to form a bond, or when we are coming to an agreement as elements, what we have to do is that I as a metal will agree to contribute some number of electrons. The negative ions also decide that, okay, I'm also going to agree to take this number of electrons. So there's a mutual agreement, right? So the number of electrons that a particular species or a particular element or a particular metal agrees to contribute in forming a bond, that's what we call its oxidation number, right? So potassium ion, for example, is K plus. It means that potassium is willing to contribute one electron in that bond, right? So the oxidation number of potassium is +1, right? That's the oxidation number of potassium. So most of these metals, right, they have their oxidation numbers. So oxidation number basically, in layman term, I'm not giving you an official definition, but in layman term, it means that when it comes to bonding, you have oxidation number with different definitions, but when it comes to bonding, is the number of electrons that I am willing to contribute in a particular bond. So when it comes to the positive ions, when it comes to the metals, right? Metals are of two types. There are two types. The type are because there are some that are willing to donate no matter the bond. They give a fixed number of electrons or oxidation number all the time. They give a fixed number of oxidation number all the time. Those are type 1 metals. Regardless of whether the other guy wants it or not, that's the number of electrons that they give, no matter what. And there is type 2, we can give varying number of electrons. They can have varying oxidation numbers, right? So they can have +2, +4, +3, plus all that. Those guys are type 2, where based on the bond, right, they know which amount to give at a particular time. Sometimes they can give +2, sometimes they can give +3, the same species. Like for example, ion 2 and ion 3. Ion 2 will give 2 electrons in a particular bond. In another bond, you can see giving an electron of 3, right? Those one are type 2. So now let's look at the periodic table and then have a picture of all these species that can be type 1 or type 2. So let me use a green color to surround it. So look very well, the ones I'm going to circle, they are the ones that are type 1 metals. So these guys are type 1 metals. So this guy, this side of the periodic table, here up to this guy. So let me close this guy. These guys are type 1 metals. Type 1 metals. And then if you go to this guy too as well, aluminum to zinc to silver, these guys are also type 1 metals. So type 1 metals means that they give fixed number of electrons, or they have fixed oxidation number. So if you say lithium is in group 1, so lithium plus is always plus. Sodium is sodium plus all the time. The ionic form of potassium is potassium all the time. Calcium, Ca2 plus. Rubidium, Rb plus. Calcium is not calcium. Why is this periodic table? It's cesium, Cs. Sorry about that. Cesium, and then barium is also Ba2 plus. So these guys are type 1. Aluminum 3 plus, Al3 plus. We have zinc 2 plus. Zinc is always 2 plus, and then silver is always Ag plus, right? So we have lithium plus, we have Ag plus. That's for silver. We have calcium 2 plus. We have zinc 2 plus. So if you come to this species that you surround it with, the metal type 1, no matter the bond, right, they don't change the oxidation number. They always give the same fixed number of electrons. Whenever you see them in a bond, these guys, you have to know that these guys are going to give that fixed number. So that's going to be very helpful. They don't change their oxidation numbers, right? So we don't struggle naming stuff with them like that, right? They don't change. But if it's the other ones, we need to, when we are trying to name in a bond in which they are found, we need to specify the oxidation number in that particular bond. Because, for example, iron, for example, if you want to name an iron, a species of an iron, Fe2O3, we also have Fe3O4, right? In Fe2O3, this iron is iron 2 plus, so the iron is giving Fe2 plus. In this particular one, where F3O4, the ion is Fe3 plus, ion alone, right? So when we are naming this species, we have to tell the oxidation number of the metal type 2. If it's metal type 2, we need to actually specify the oxidation number. But if it's the metal type 1, we don't have to bother. Something like when we saw an example like sodium chloride. You see, when it comes to sodium is a type 1 metal. So when we are naming, we just say sodium chloride. Sodium. You don't have to say sodium 1 chloride. This doesn't happen because sodium is a metal type 1. So in this session, we need to just basically understand which are data type 1, which are metal type 1 and metal type 2. So know the metal type 1, and then anything aside the metal type 1 is a metal type 2. And then for naming those ones, we need to specify the oxidation numbers. And we say what oxidation numbers are. They are just the number of electrons that a particular metal would like to donate in a particular species. The agreement that they want to contribute to forming the bond, right? So that is it for this session. So I hope that at the end of this session you understand the clear difference and know the examples of metal type 1s and metal type 2. We move on, continuing on this journey of IUPAC nomenclature. See you in the next session.